Okay. I hope you have got the information that you'll be having contact classes. Contact classes start ചെയ്യാൻ വേണ്ടി യൂണിവേഴ്സിറ്റി തീരുമാനിച്ചു. ഇനി ഗവൺമെന്റിന്റെ കയ്യിൽ നിന്ന് അപ്രൂവൽ ആയി കഴിഞ്ഞു കഴിഞ്ഞാൽ യു വിൽ ബി ഹാവിംഗ് കോൺടാക്ട് ക്ലാസ്സസ്. എനിക്ക് തോന്നുന്നു നിങ്ങളുടെ ഷെഡ്യൂൾ പ്രകാരം ജനുവരി പകുതി എങ്ങാണ്ടാണ് കോൺടാക്ട് ക്ലാസ്സസ് സ്റ്റാർട്ട് ചെയ്യുന്നത്. കോൺടാക്ട് ക്ലാസ്സസ് മെയിൻലി ഫോർ ഡിസ്കഷൻ ഓഫ് ഓൺലൈൻ ക്ലാസ്സസ്, പിന്നെ അതുപോലെ നിങ്ങളുടെ ലാബ് സെഷൻസ്, ഇത് രണ്ടിനും വേണ്ടിയിട്ടാണ് മെയിൻലി ആ കോൺടാക്ട് ക്ലാസ്സസ് തീരുമാനിച്ചിരിക്കുന്നത്. ആൻഡ് ഐ തിങ്ക് യുവർ എക്സാംസ് വിൽ സ്റ്റാർട്ട്, regular exams will start by March first week, and then you will have the next semester by April first week. അങ്ങനെ എന്തോ ആണ് അതിന്റെ ഷെഡ്യൂൾ. ഐ തിങ്ക് ഇറ്റ് ഈസ് ദർ ഇൻ വെബ്സൈറ്റ്, ഐ എം നോട്ട് ഷുവർ. അപ്പം കോൺടാക്ട് ക്ലാസ്സസിൽ അപ്പം നമുക്ക് ഇതിപ്പം മോഡ്യൂൾ നമ്പർ 3 ആണ്. നമുക്ക് ഒരു മോഡ്യൂളും കൂടി ഉണ്ട്, മോഡ്യൂൾ നമ്പർ 6, that is wave guides. I think I need maybe like 4 lectures for finishing that. So what I would do is I think next week we will be having this vacation, Christmas vacation. So I'll try to upload these videos for the next module also. And in case if you doesn't get online classes, we will discuss those videos during the contact class hours. Okay. അപ്പോൾ അത് വീഡിയോസ് ഇഗ്നോർ ചെയ്യരുത്. മേക്ക് ഷുവർ യു സീ ദ വീഡിയോസ്, ബിക്കോസ് അത് നോക്കാതെ വന്നു കഴിഞ്ഞാൽ നമ്മുടെ ഡിസ്കഷനിൽ യു വിൽ നോട്ട് അണ്ടർസ്റ്റാൻഡ് എനിത്തിങ്. ഓക്കെ. സോ അതാണ് ഇപ്പോഴത്തെ പ്ലാൻ. And we'll also solve a lot of problems if we get time. Karanam, we have just said theory and just move through, but we need to solve some problems. Okay, so let me look at. So this is normal incidence. Upon endana incidence, normal incidence അല്ലെങ്കിൽ oblique incidence എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നമ്മൾ സാധാരണ രീതിയിൽ ബൗണ്ടറി കണ്ടീഷൻസിൽ when we had looked at electrostatic and magnetostatic boundary conditions, we told that ഒരു ബൗണ്ടറി, രണ്ട് ഡിഫറെന്റ് മീഡിയം വന്നു കഴിഞ്ഞു കഴിഞ്ഞാൽ ആ ബൗണ്ടറിയിൽ വാട്ട് വിൽ ഹാപ്പൻ, അല്ലെങ്കിൽ വാട്ട് വിൽ ബി ദ ചേഞ്ച് ഇൻ ഇലക്ട്രിക് ആൻഡ് മാഗ്നറ്റിക് ഫീൽഡ്സ് അക്രോസ് ദ ബൗണ്ടറീസ്, അത് നമ്മൾ കണ്ടതാണ്. അതേപോലെ തന്നെ ഇലക്ട്രോമാഗ്നറ്റിക് വേവ് ഒരു പർട്ടിക്കുലർ മീഡിയത്തിലൂടെ പ്രൊപ്പഗേറ്റ് ചെയ്ത് മറ്റൊരു മീഡിയത്തിലേക്ക് കടക്കുമ്പോൾ അതിന്റെ ഇലക്ട്രിക് ഫീൽഡ്സിനും മാഗ്നറ്റിക് ഫീൽഡ്സിനും എന്തൊക്കെ ചേഞ്ച് വരാം, അതാണ് നമ്മുടെ നോർമൽ ഇൻസിഡൻസും ഒബ്ലിക് ഇൻസിഡൻസും കൊണ്ട് വി ആർ ട്രൈങ് ടു ഫൈൻഡ് ഔട്ട്. അപ്പൊ അതിനു മുമ്പ് വി ആർ ജനറലൈസിങ് ദ വേവ്. ഇതുവരെ നമ്മൾ പറഞ്ഞത് വേവ് ഈസ് പ്രൊപ്പഗേറ്റിംഗ് ഇൻ സെഡ് ഡയറക്ഷൻ, ഇലക്ട്രിക് ഫീൽഡ് എക്സ് ഡയറക്ഷനിലാണ്, അതുപോലെ മാഗ്നറ്റിക് ഫീൽഡ് വൈ ഡയറക്ഷനിലാണ് എന്നൊക്കെയാണ്. നമ്മൾ ഇതിനെ കുറച്ചുകൂടി ജനറലൈസ് ചെയ്യുന്നു. അതായത് എ ക്യാപ് ഇ എന്ന് പറയുന്നത് വി സേ ഇറ്റ് ഈസ് ദ ഡയറക്ഷൻ ഓഫ് ഇലക്ട്രിക് ഫീൽഡ്, എ ക്യാപ് എച്ച് എന്ന് പറഞ്ഞ ഡയറക്ഷൻ ഓഫ് മാഗ്നറ്റിക് ഫീൽഡ്, എ ക്യാപ് കെ എന്ന് പറയുന്നത് ഡയറക്ഷൻ ഓഫ് പ്രൊപ്പഗേഷൻ. അങ്ങനെയാണെങ്കിൽ വാട്ട്സ് ദ റിലേഷൻഷിപ്പ് ബിറ്റ്വീൻ ത്രീ ഓഫ് ദം? Basically, we know that all three are perpendicular to each other. So if this is the electric field, this is the magnetic field, and this is the direction of propagation, all are perpendicular. അങ്ങനെയാണെങ്കിൽ we can relate them using the cross product. Okay, E cross H K ആയിരിക്കും, H cross K E ആയിരിക്കും, K cross E H ആയിരിക്കും. Okay, so നമ്മളൊരു എക്സാമ്പിൾ കണ്ടു. ഇവിടെ ഒരു സെഡ് എടുത്തു കഴിഞ്ഞാൽ സെഡ് ഡയറക്ഷൻ ആണെങ്കിൽ പ്രൊപ്പഗേഷൻ, അതുപോലെ ഇലക്ട്രിക് ഫീൽഡ് എക്സ് ഡയറക്ഷനിലാണെങ്കിൽ വി വിൽ സീ ദാറ്റ് വെൻ യു ഡു ദ ക്രോസ് പ്രൊഡക്റ്റ് യു വിൽ ഹാവ് ഇറ്റ് ഈസ് ഇൻ വൈ ഡയറക്ഷൻ. ദെൻ വി ഹാവ് സം മെത്തേഡ്സ് ടു ലുക്ക് അറ്റ് ദ ലൈക്ക്, ബിക്കോസ് ഇത് 3D പ്രൊപ്പഗേഷൻ ആണ് ഇലക്ട്രോമാഗ്നറ്റിക് വേവ്. അപ്പോൾ 3D വെക്ടർ അല്ലെങ്കിൽ ഡയമെൻഷനിൽ നമുക്ക് ഇതിനകത്ത് വരയ്ക്കാൻ കുറച്ച് പ്രയാസമാണ്. സോ വാട്ട് വി ഡിഡ് വാസ്, the direction can be of two types, either into the plane of paper, that is ഇങ്ങനെ ഒരു ആരോ ഉണ്ടെങ്കിൽ ഈ ആരോയുടെ ബാക്ക് സൈഡ് ഇവിടെ നമ്മൾ വ്യൂ ചെയ്യുമ്പോൾ you see that it is a cross that is into the plane of paper. Similarly, if the arrow is coming towards you, then if you view from here you see there's a dot, that is the dot here. Okay, so those are two different directions. പിന്നെ നമ്മൾ പറഞ്ഞു how we can find the direction of any of the parameters if you are given the other two. For example, നിങ്ങൾക്ക് a electric field ന്റെ ഡയറക്ഷനും പ്രൊപ്പഗേഷന്റെ ഡയറക്ഷനും തന്നിട്ടുണ്ട്. അങ്ങനെയാണെങ്കിൽ h ന്റെ ഡയറക്ഷൻ കാണാൻ you just curl your fingers from K to E. So the direction of your thumb will give you the direction of h. Similarly, ഈ കേസിലാണെങ്കിൽ if you curl your fingers from K to E, the right hand fingers, then you can see that the direction will be into the plane of paper, and that's why we got as cross. Okay, now അതാണ് basic things. ഇനി നമ്മൾ പറയാൻ പോകുന്നത് the wave is incident normally. Normally means perpendicular to the boundary. So you have said here x here and the y is here. The boundary is infinitely long. Actually it moves infinitely. Okay, now the wave is incident. When the wave is incident, some part of the wave is reflected, some part is transmitted. Okay, and so so the direction of propagation is in z direction, and we assume that the direction of E is in x, so that the corresponding direction of H will be in y. Similarly, you have directions for the transmitted and the reflected wave. But transmitted wave in directions orientation എല്ലാം സെയിം ആയിരിക്കും. പക്ഷെ റിഫ്ലക്റ്റഡ് വേവിന് പ്രൊപ്പഗേഷൻ ഡയറക്ഷൻ നമ്മുടെ ഓപ്പോസിറ്റ് ഡയറക്ഷനിൽ പോകുന്നത് കാരണം അതിന് കറസ്പോണ്ടിങ് ആയിട്ട് ഇലക്ട്രിക് ഫീൽഡിന്റെയും മാഗ്നറ്റിക് ഫീൽഡിന്റെ ഡയറക്ഷൻസ് മാറും. ഓക്കെ, സോ യു സീ ദാറ്റ് ദർ ഇസ് എ ചേഞ്ച് ഇൻ ഡയറക്ഷൻസ്. ഇലക്ട്രിക് ഫീൽഡ് സെയിം തന്നെ ആയിരിക്കും, പക്ഷെ മാഗ്നറ്റിക് ഫീൽഡിന്റെ മാറും. ഓക്കെ, ഫൈൻ. നൗ what we want to find is, there is incident in ഓരോ വേവിനും, ട്രാൻസ്മിറ്റഡ് വേവ്, ഇൻസിഡന്റ് വേവ്, റിഫ്ലക്റ്റഡ് വേവിന് ഓരോന്നിനും there is an electric and a corresponding magnetic field. അപ്പം അത് തമ്മിലുള്ള റിലേഷൻ എന്താണ്? that is what we are going to find out. But അതിന് ഇമ്പോർട്ടന്റ് ആയുള്ള കാര്യം, you see that this is the boundary. Okay, so if the electric field is in the direction, that means it is parallel to the boundary. Similarly, the magnetic field is also parallel to the boundary. The direction of propagation is perpendicular to the boundary. Okay, കാരണം ഇതാണ് നമ്മുടെ ബൗണ്ടറി, ഇതിലേക്കാണ് വേവ് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്നത്, സോ ഇറ്റ് ഈസ് പെർപെൻഡിക്കുലർ. പക്ഷെ ഈ സെയിം ബൗണ്ടറിയിൽ യു സീ ദ ഇലക്ട്രിക് ഫീൽഡ് ഇസ് ലൈക്ക് ദിസ് ആൻഡ് ദ മാഗ്നറ്റിക് ഫീൽഡ് ഇസ് സംതിങ് ലൈക്ക് ദിസ്. So it is actually parallel to the boundary, or it is tangential to the boundary. Okay, so that information is very important because we are going to make use of that information in deriving the relations. So incident wave. So we know that the electric field can be represented in terms of the magnitude into e raised to minus gamma propagation constant into e raised to j omega t. e raised to j omega t നമ്മുടെ എല്ലാ ഇക്വേഷനിലും വരും. So we are just ignoring that. We are not taking into consideration. So we define a term EIS as EI0 e raised to minus gamma 1 z. എന്തുകൊണ്ട് gamma 1? Because it is in the first medium. Second medium അത് gamma 2 ആവും. Okay, കാരണം propagation constant എന്ന് പറയുന്നത് to be different for different medium. And E is in x direction. So you see that E is in x direction. And for the incident wave, the H is coming like this. So the Y is also like this. So H and Y are in the same direction. So it is positive. So ഇത് നമ്മൾ ഡിറൈവ് ചെയ്തതാണ് കഴിഞ്ഞ കുറെ ക്ലാസ്സുകൾക്ക് മുമ്പ്. അതായത് ഇലക്ട്രിക് ഫീൽഡിന്റെ ഇക്വേഷൻസ് ഇങ്ങനെ ഇരിക്കും, അതിന്റെ കറസ്പോണ്ടിങ് മാഗ്നറ്റിക് ഫീൽഡിന്റെ ഇക്വേഷൻസും ഇങ്ങനെ ഇരിക്കും. And we can relate the magnitude EI0 and HI0 by the relationship. The ratio of EI0 by HI0 is eta1. Eta1 and it is in the first medium. Eta1 is the intrinsic impedance. Intrinsic impedance will be different for different medium. So since it is in the first medium, you have eta1. So I can generally write HIS and EIS something like this. Okay. Similarly for reflected wave no change in the now the wave is traveling towards minus z direction. So instead of e raised to minus gamma 1 z, it will be e raised to plus gamma 1 z because z is in minus direction. Okay, and the value of h, now h is now cross, means it is propagating into the plane of paper, but your y direction is out to the plane of paper, because of which there will be a minus sign for the h. So you will still able to relate ER0 and HR0 by eta1. So this is the relation. So you get the relations the reflected wave. Okay, so in medium 1, the total electric field is basically sum of electric field of incident and reflected wave. And similarly, sum of magnetic field is the total magnetic field in medium 1. ഈ രണ്ട് കേസിലും electric field and magnetic field is parallel to the boundary or tangential. Okay, that is the important thing. And if you go to look at transmitted wave, you see transmitted wave is propagating along positive z. So there is this is e raised to minus gamma 2 z, gamma 2 y, because it is in the second medium. And you see that E is in this direction, x direction, and you have the magnetic field which is in y direction, which is positive y. So you'll have a cap x and a cap y. Now you can relate the magnitude E T0 and HT0 by ET0 by eta 2 is. So this is the relation. So in the medium 2, you will have only one particular wave, which is a transmitted wave. And again, the transmitted wave, electric field, magnetic field is parallel to the boundary. Okay. So the boundary conditions are like this. So E boundary conditions are already derived. I think it was in module 1. Electric field in magnetic field in boundary conditions. So actually the difference of the tangential component is equal to rho v or rho s. Okay, but we are assuming it is a source free medium. Rho v and rho s is 0. So we can have E1 tangential is equal to E2 tangential, H1 tangential is equal to H2 tangential. So I can write E1 as the, so this is the tangential component in the first medium, this is the tangential component in the second medium. അതുപോലെ magnetic field tangential component ഇതാണ്, magnetic field tangential component ഇതാണ്. Okay. Now the important thing here is ഒരു plane. If you consider this plane, ഈ plane z ന്റെ value 0 ആണ്. Okay, because the origin of, so if you look at any part of this plane, the value of z is equal to 0, because z will change only along this direction. Okay, so basically you can say that the wave is incident at z equal to 0. So your equation will be very simple, because we need to consider only those equations or values in which if you substitute z equal to 0, what is the value? Okay, so wherever it is the AI, HI, ER, HR, ET, HT, for all these values, we want to find at the boundary what is the change. So at the boundary, the value of z is 0. So when the value of z is 0, you can just substitute for the value of z equal to 0. So the equations will become very simple. Okay, so you just substitute. So here EI of 0 means you are saying substituting z equal to 0. So you substitute z equal to 0. So you'll have a simple equation. Similarly for H1 also you have a simple equation, and H2, E2 also you have a simple equation. Now you substitute for this in this equation. Okay, EI plus ER is equal to ET, HI plus HR is equal to HG. When you substitute it, now you will get two different equations, and you can solve the equations to find out what is the relation between the incident and the reflected wave, or the magnitude of incident and the reflected wave, the magnitude of incident and transmitted wave. That magnitudes will be in terms of electric field, or you can also write in terms of magnetic field, but here we are writing in terms of electric field. So when you solve the equation, you see that your electric field will have something, the relation between transmitter and incident wave is something like this. This is called as transmission coefficient, and it gives you how much of the incident wave is transmitted. In the already transmission lines similar equation. Otherwise, reflection coefficient otherwise transmission coefficient but we are looking at how much amount of transmission, അതായത് ഒരു വേവ് ഇൻസിഡന്റ് ചെയ്തു കഴിഞ്ഞാൽ എത്രത്തോളം വേവ് ട്രാൻസ്മിറ്റ് ചെയ്യുന്നു എന്നുള്ളതിന്റെ ഒരു എമൗണ്ട്, ഒരു ക്വാണ്ടിറ്റേറ്റീവ് വാല്യൂ ആണ് ഈ ട്രാൻസ്മിഷൻ കോഎഫിഷ്യന്റ്. But it is related using the intrinsic impedances of first and second medium. Okay, simple equation. Similarly, when you solve and substitute for all these things in a different way, you will get a relationship in terms of the ratio of reflected and incident wave. This is called as a reflection coefficient. Okay, and it says how much of incident wave is reflected. And this is also in terms of the intrinsic impedance and of medium 1 and medium 2. Now you see the reflection coefficient can be made 0 by making the intrinsic impedance same. If both are same, the reflection coefficient is 0, which means all the incident wave will be transmitted. Okay. I hope you have I hope you have looked through the lecture. I am not sure. So if you have any doubts in this, you can ask me now. Instant normal instance is very simple. Exam make sure you do that because it is very simple. Oblique instance is a bit tough. Any doubts? If you don't have any doubts, I will move to the next lecture. Okay, because I am planning to have a quiz during once you come back. So make sure you watch all these videos. Okay, fine. So I'll go into the next lecture. This is oblique incidence. Oblique incidence need to that is moving along any of the particular axis, and it is incident on some boundary. You have the electric field in some x direction or y direction. The magnetic field is in some y direction, something like that. So all wave, electric field, magnetic field is real life scenario, a practical scenario, it is not possible. Because the wave can travel in any arbitrary direction. Now, when the wave travels in arbitrary direction, how are we going to make use of all these equations to find out the relationship between electric and magnetic fields in two different medium after the boundary? So അതിന് വേണ്ടിയിട്ട് basic stuff change ചെയ്യാനുണ്ട്. So there is something called as a wave vector or a propagation vector, which is called as k. And k, depending on the direction of propagation, the k vector will change. For example, if the wave is propagating in x direction, or let's say z direction, okay, then your k value will have only z component. Okay, and actually this k z, which is the magnitude or the component along z, will be the phase constant beta 1 in medium 1. Okay, so now the wave is propagating in some arbitrary direction which may not be in x, y, or z. So in that case, it can have components along all the x, y, and z directions. So you can write the k vector as something like this. Okay, now we have written this is cos of omega t minus k dot r. Okay, but the cos of minus theta is cos theta, so it doesn't matter whether you write omega t first term or second term. Okay, and also we wrote as cos because actually the solution is real part of e into e raised to j omega t, something like that, EIS. Okay, so because of which we will get cos. Okay, you can write in terms of directly in terms of e raised to j k dot r minus omega t. ഇങ്ങനെ എഴുതിയാലും കുഴപ്പമില്ല, ഞാൻ കുറച്ചുകൂടെ എളുപ്പത്തിന് വേണ്ടി ഇങ്ങനെ എഴുതുന്നേ ഉള്ളൂ. Okay, now k is some vector. It's called as a wave number vector or propagation vector. R is called as a position vector, and it doesn't change. K change ചെയ്യാം, പക്ഷെ R എന്ന് പറയുന്നത് എപ്പോഴും ഇത് തന്നെയായിരിക്കും. X ax cap plus y ay cap plus z az cap. Okay, so the k dot r will have you. So I hope you know how to take the dot product. K dot r means you take the product of kx into x plus ky into y plus kz into z. That is your k dot r. That's a constant. And so I have just given an example by taking some value of kz and population vector and all. Okay, fine. Now let's look at the oblique incidence, or let's analyze that k further. So you see that there is a axis z. The medium is between x-axis. So on the left side there's a medium 1, on the right side there is medium 2, and those two mediums will have different parameters. And this plane is z equal to 0 plane. Okay, the wave is incident on this plane. Now the wave is propagating in some arbitrary direction. So it has a vector ki Wave is reflected in some arbitrary direction. Wave is transmitted in some arbitrary direction. Okay. Now, this complete reflection transmission or the wave propagation is along a plane. E plane is wave propagation. So this plane is called as plane of incidence. Okay. So, നമ്മുടെ ഇപ്പം ഈ ഒരു പേപ്പറിന്റെ പ്ലെയിനിലാണ് ഈ വേവ് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്നത്. ഇത് every time it might not be true because for the simplicity we have taken that the plane of paper is the plane of incidence. Okay. So don't confuse with this plane. This is not the plane of incidence. The plane of incidence is the plane in which the wave is propagating. This is called as a plane of incidence. Okay, and so since the wave is propagating in some arbitrary direction, it will make an angle with Z for incident, reflected, and transmitted wave. Or angle it will make. Okay. Now we are considering a lossless medium. So if you are considering a lossless media, then the magnitude of this k vector will be the corresponding phase constant. So for medium 1, the magnitude of ki is same as magnitude of kr is equal to beta 1. Similarly, for medium 2, the magnitude of kt is equal to beta 2. That we have already mentioned here. Okay. Now, what we want to do is we want to find the component of each of these propagation vectors along any of the axes. Basically, we want to resolve ki, kr, and kt along z and x, and if possible y. But here we will not be able to get y. So how will you do this? So ki എന്ന് പറയുന്നത് ഇങ്ങനെയാണ്. Okay, this is like this. Okay, and if you look at ki, you see this angle is theta I. Okay, the two parallel lines in the angle same ആയിരിക്കും. Okay, so this is theta I. So the component along the z axis, because z axis is in this direction, and you want to find the component in this direction. So you look at theta I. So the component of the side of the triangle which is adjacent to theta I will have a cos. So this will be actually beta 1 or magnitude of kiz into cos theta I. And this is opposite side of theta I. So അതിന്റെ component on the sin ആയിരിക്കും. So magnitude of kx into sin theta I. Okay. Similarly, you can find the components along each of the waves. Okay, so that we will see in detail in future things. So here, for example, this is kr in this direction. Okay, and you can resolve into two components, one along x and one along z. This is basically your vector addition. Okay, so one along x is okay, so if you resolve into two components, you see that this angle will be theta. Okay, so this is theta. So this, you see this is in this direction, which means it is in the minus z direction because z is in this direction and this is in this direction. These are minus. But theta r is adjacent to this side. So this will be cos theta r. But since it is direction is opposite to that of z, you will have minus. Now for x component, it is in the positive direction of x because x is in this direction, which is upwards. So this is also upwards. So that is in the positive direction of x. And you see that it is in the opposite side of theta. So you have sin theta. And the magnitude is beta because we are considering a lossless medium. Similarly, for transmitted wave, the k is in this direction. You can resolve into two components, one along parallel to z, one parallel to x. Both are in positive directions of x and z. And you will have theta t here because you see that this is theta t. Okay, and so the z is direction is parallel or adjacent to theta t, so you'll have cos, and x is opposite to theta t, you will have sine. So that is sine theta t, cos theta, beta 2 because of the magnitude. So you can resolve the components. Similarly, the electric field can be expressed in terms of this k dot r minus omega t. Okay. Now, for satisfying the boundary conditions, actually you can have different frequencies, omega 1, omega 2, omega 3. Okay. But for the wave to exist in both the media, it needs to satisfy the boundary conditions. And to satisfy the boundary conditions, the only possible way is that all the values of kix and kiy should be same. Now, since the wave is propagating along some, or the boundary is along z equal to 0 and the wave is propagating in xz plane, it need not be that ki is z and kr z and k is need to be equal, but all the other components should be equal. There is a big derivation for this. Currently, I don't think you need that derivation. Okay, and so with this in mind, now you say that kix is equal to krx. We already found kix here. This is ki sin theta I. We already found krx here, which is beta 1 sin theta r. So beta 1 sin theta I is equal to beta 1 sin theta r, which is from this equation. So you see beta 1 will get cancelled, and sin theta I should be equal to sin theta r. And the only possible way in which you can get theta I, this relationship to satisfy, is by having theta I is equal to theta r. That means your incident angle should be equal to the reflected angle. Okay. Similarly, you have another relation, kix is equal to ktx, and kix is beta 1 sin theta I, which we have already derived. Ktx is equal to beta 2 sin theta t. So if you do that, then you see that there is, although in the previous case you have beta 1 in both sides, but in this case you have beta 1 here and beta 2 here, so you can't get it cancelled. But for a lossless medium, we have derived that the value of beta 1 is omega into root over mu 1 epsilon 1, and the value of beta 2 is omega into root over mu 2 epsilon 2. Okay, so you can take the ratio of, you can bring sin theta t to this side and beta 1 to that side. So sin theta t by, or the other way, sin theta t by sin theta I is equal to beta 1 by beta 2, which is root over omega 1 mu 1 epsilon 1 by root over mu 2 epsilon 2. And this is actually the phase velocity. So 1 by root over mu 1 epsilon 1 is equal to u1, and 1 by root over mu 2 epsilon 2 is equal to u2. This is actually the velocity of the wave. Okay, but you can still do some more manipulations. You can bring this here and bring this here, so you'll get equation something like this. You multiply by c on both sides, and this expression c into mu 2 root over mu 2 epsilon 2 is called as the refractive index of the medium 2, and c into root over mu 1 epsilon 1 is equal to n1 is a refractive index of medium 1. So you can write n2 sin theta t is equal to n1 sin theta I. This is called as Snell's law. Okay, so this is the basic things before we go into oblique incidence. Okay, and so understanding this will help you in understanding the future part. So anybody have any questions? Oblique incidence കുറച്ച് ടഫ് ആണ്, കാരണം കുറച്ചധികം mathematical things വരുന്നുണ്ട്. But once you know any one particular derivation, it is easier to derive all other things. അപ്പോൾ ആദ്യത്തെ അല്ലെങ്കിൽ ഈ ഒരു പാർട്ട്, ബേസിക് പാർട്ട് നന്നായിട്ട് മനസ്സിലാക്കുക, എന്നിട്ട് ആദ്യത്തെ ഒരു ഏതെങ്കിലും ഒരു ഡെറിവേഷൻ നന്നായിട്ട് മനസ്സിലാക്കി കഴിഞ്ഞാൽ ഇറ്റ് ഈസ് വെരി ഈസി. ഓക്കെ ഓക്കെ, സോ ഐ വിൽ മൂവ് ടു ദ നെക്സ്റ്റ്. I think okay, so in this part you are going to derive the expression for electric, or the relationship between electric and magnetic fields in all these mediums, or for all the waves. So this is just a recap of how it is being done. Okay, I'm not doing it anyway. Okay, now you see that you can have this as direction of propagation, and you have electric field like this and magnetic field like this. Now there are two possibilities. One is electric field is in the plane of incidence. So this is the plane of incidence, and you see the electric field is in this plane. That is one possibility. The other possibility is electric field is perpendicular to the plane of incidence. It will be something like this. Okay. So in this, we are considering the electric field is in the plane of incidence, and this is called as parallel polarization. Now, you should not confuse this polarization with our circular and elliptical and etc. So that is totally different. This we are saying that there is a polarization, or there is some kind of a separation between. We are considering two different scenarios. The first scenario is in which your electric field is in the same plane as that of the plane of incidence, which is this plane. And the second scenario, we consider electric field is perpendicular to the plane. Okay, but if you understand the derivation of one, you can easily understand the derivation of the second one. Okay, fine. So the wave is propagating in this direction. It is getting incident. Some wave is getting reflected. Some wave is getting transmitted. For the incident wave, you have Ki. For the reflected wave, you have Kr. And for the transmitted wave, you have Kt. This is your propagation vector. So for the incident wave, the E is in this direction, and the corresponding direction of Hi is towards you. For the reflected wave, the E is in this direction, and the corresponding direction of the H is away from you into the plane of paper. For the transmitted wave, E is in this direction, and your corresponding H is pointing towards you. Now the question you might ask is, how will you determine the direction of E? That I can have this something like this also. Why did I choose this? Okay, or for transmitted wave, instead of this direction, I can have E in this direction. Why did I choose this? Okay, so you can choose any such direction. That is up to you. Only thing is the E should be perpendicular to the direction of propagation. I chose to have E in this direction because it is easy for me to find the calculations. You can do in any directions. That is totally fine. But then you need to derive it according to that. Okay. So depending on the E direction, your H direction will also change. So for example, if the E you take is like this direction, then your H is something like this. Similarly, if you take E in this direction, your H will be something like this. So depending on E, the direction of E that you take, your H will change. Okay, fine. Now, okay, let's take EI. EI is in some arbitrary direction. You need to find the components of EI along X and along Z, or parallel to X or parallel to Z. Okay, so EI is in this direction. So if you resolve it into two components, one is this and one is this. Okay, so along minus X, minus Z, there is one component, and along plus X, there is another component. And you see that this angle is theta. Okay, so you can this is actually a pretty, what do you call, geometrical thing. So this is theta, this is 90 degree, and so this is 90 degree plus theta, or else you can do something like this. So there is this angle, this is parallel line, so this is theta I, so this is 90 minus theta I. Okay, so basically you will have, so if you create a triangle like this is 90 minus theta I, so this will be theta I. Okay, so that is your basic geometry. Fine. Now, so this is theta I, so the X component is opposite to theta I, so this will be sine, and the Z component is opposite to theta I, so this will be sine, and the X component is along or on the side of theta, so this will be cos. So the Z component is in opposite direction, so there will be a minus, and the X component is in positive direction, so there will be plus. So this is how EI is. KI said we have already derived in the last PDF. Okay. Now, if you write the value of E, we write as EIS, it will be EI0 multiplied by the sum of the components, which is the total EI, which is cos theta. So you take the sum of these two. So EI0 into cos theta AX cap minus EI0 sin theta AZ cap, which is this, into e raised to minus j k1 dot r, ki dot r. So ki, we have already found beta 1. So beta 1 is the magnitude into the sum of these two components. So that is this. Now, when you do dot r, you will have an x into x sin theta plus z into cos theta. Because r is this one, you do the dot product. And so the final equation will be something like this. Okay. And HIS. So this is along the y direction. So y direction is something like this. Okay, so because it is in the y direction, you don't want to resolve into any components. You can directly write as HIS as HI0 into something, but it will be, you can write in terms of EI0. So EI0 by eta 1, and whatever this term is there, it will be same as that of E. Okay, because it is for the same wave. So this is actually for the propagation. So propagation is direction is same for EIS and HIS for the incident wave. Okay. Similarly, for reflected wave, the E is in this direction. You resolve into two components along Z and along X. Z is positive, X is positive. Now theta R is this. Okay, and so since Z is opposite to theta R, this will be sine, and since X is adjacent to theta R, this will be cos. Since both are in positive direction, you will have plus cos theta R and plus sin theta R. Okay, so you can write ERS as ER0, the sum of those two terms. Now KR, we have already seen that it is in this direction. This direction, you can resolve into two components along minus Z and plus X. So this is sin theta R minus cos theta R. So you write KR dot AR. So KR has magnitude beta 1. This is sin theta R minus cos theta R dot R. So this will be the final KR dot R. So you'll have the final equation like this. Okay, and then HRS will be ER0 by eta 1. Now HRS is towards the plane of paper. The Y is like this, the HR is something like this, towards the plane of paper. So because of it, it will be minus. So there will be a minus sign for HR. Okay, fine. So we found that for HR and ER. Now ETS is for transmitted wave. So ETS is something in this direction, like this. You resolve into two components along minus Z and along plus X. Okay, so and the theta T is like this. So you'll get ETX and ETZ as something like this. So ETZ will have minus sign because it is in the opposite direction of Z. And so you'll get ETS as something like this and HTS as something like this. You apply boundary conditions. Basically, you found the magnitude of E and along tangential component and magnitude of magnetic field in both medium, that should be equal. Okay, so the question is, what is the tangential component? Now you see that if you when you did this component, which is along Z, is perpendicular to this boundary, something like this. But all other components, whether it is Y or X, it is parallel to this boundary. Only Z is perpendicular to this boundary. So you find the components in each of the waves which is along X or along Y in this tangential component. So for E in the first medium, you have two ERX and EIX. So ERX is E0 e raised to minus j beta, all these things, because you see that in this one, this is perpendicular component and this is tangential component. So basically your tangential component is this multiplied by this. And similarly for HIS, it is along Y, it is the whole thing is tangential. Okay. Similarly for ERS, this component multiplied by this is tangential. HRS is completely tangential. For ETS, this component multiplied by this is tangential. HTS is completely tangential. So you can write the equations for tangential components, and we are evaluating at z equal to 0. Why? Because the boundary is at z equal to 0. So this boundary is at z equal to 0. So you don't want to consider for any other values. So when you evaluate at z equal to 0, then you will have ERX plus EIX is something like this. Similarly, in medium 2 also will get something like this. The tangential magnitude of tangential component should be same. So magnitude of this should be equal to the magnitude of this. Now, when you take the magnitude of this, you see that this is e raised to j theta. Magnitude of e raised to j theta is 1. So we can directly substitute it as 1. Similarly, there is a magnitude here which is equal to 1. So finally, you will end up in this equation. Okay. So I haven't given this equation directly from the lecture. You can try to derive this. It is exactly the same as what I have derived for the first one. Okay. And then you do some manipulations, you solve the equations, and you find out the relationship between EI0 and ET0. And when I do ET0 by EI0, you will get this expression. This is called as the transmission coefficient for parallel polarization. Okay. Similarly, when you do manipulations to the same equations again in a different way, you will be able to find out the reflection coefficient for parallel transmission. It will be something like this. And you can see that you can relate reflection coefficient and transmission coefficient for parallel polarization. You can just do it as a homework because you can directly write the equations of reflection coefficient and transmission coefficient and substitute in these equations and see whether the right hand side is equal to left hand side. Okay. Now for reflection coefficient, you see when you make this equal, these two terms, then the reflection coefficient is 0. That means there is complete transmission, there is no reflection. Now the angle of incidence at which the complete transmission is happening is called as the Brewster's angle. That is, it is called as theta is equal to theta b parallel. Now, so the condition is eta 1 cos theta t should be equal to, sorry, eta 2 cos theta t should be equal to eta 1 cos theta I. Okay. Now you can square this terms and you can find the expression for sine square theta b Brewster's. And you will find the equation something like this. So this is also a homework to derive this equation. To deriving, you need to use the intrinsic impedance as root over mu2 by epsilon 2. Intrinsic impedance of first medium is root over mu1 by epsilon 1. And then you also know that sine theta t by sine theta I is equal to root over mu2 epsilon 2 by, sorry, mu1 epsilon 1 by mu2 epsilon 2. This we have derived in the last lecture. So if you substitute everything in this one, then you will get this equation. Now for a non-magnetic medium, mu1 is equal to mu2 is equal to mu0. So in that case, your Brewster's angle will be sine theta b is equal to root over epsilon 2 by epsilon 1 plus epsilon 2. Okay. So make sure you do all these homeworks. Homework there is a significance for that. Make sure you do this homework because it will make you understand the previous derivations because both the derivations are related. And it will help you for your exams because they have asked derivations multiple times. Okay. So this is for oblique incidence for two mediums. So if you have any doubts, let me know. Okay, fine. So make sure you see the lecture video. Lecture video കാണാതെ വന്ന് ഞാനിപ്പോൾ പറയുന്നത് കേട്ട് കഴിഞ്ഞാൽ I don't think you will understand. So make sure you go and watch the video. It is very important to look at that video. Okay, fine. So I think we will stop the class here. I think there is one more thing, oblique incidence 3, that we will do in I think either we can do in some separate special class, or we can do once we come back, whichever is convenient to you. Okay, but anyway, so ഞാൻ പറഞ്ഞ പോലെ വേവ് ഗൈഡിന്റെ വീഡിയോസ് ഞാൻ അപ്ലോഡ് ചെയ്യും. So make sure you watch the videos. അത് കഴിഞ്ഞ് once you come back for contact classes, then we will discuss more about the subject and we'll do so more problems. Okay, fine. Okay, so then let's take the attendance. So roll number 1, absent down.
1.
Okay.
2.
Okay.
2.
3. 4. Okay.
5.
Okay.
6.
Okay.